The power of the wind is amazing. Just a moderate increase in speed can double the power output. But the wind seldom does what we want, so I'm experimenting with wind that we can control. The wind in front of my truck!
The equation for wind power predicts an exponential increase with velocity. At highway speeds, our 1.2 meter turbine should get over 10,000 watts of wind. But something called the Betz limit, explored in an earlier video, limits us to just 59% of the available power. That still leaves us with around 6,000 watts. I've spent much of my summer testing cheap wind turbines rated for just hundreds of watts, and none of them measured up. But to really check this math, we're going to need something bigger. Much bigger. Oh my word. This thing is huge. I was picturing something about a third of that size by the picture online, but wow. Okay, let's hook it up. Now we might be tempted to connect a turbine directly to the end of the generator shaft, but the bearings inside are designed mostly for radial loading, which basically means from the side. But wind turbines, in addition to spinning, they're also taking a lot of thrust load in the direction of the wind. Basically, you can picture it as if it was just a big round disc that the wind could push on. And that kind of loading could really shorten the life of the bearings inside of our generator. So we're going to design a custom hub with tapered roller bearings which can handle loads in any direction. The first step is machining the housing that will hold the outer bearing race and mount to the truck. Of course, we also want a rubber seal in there so the bearing grease doesn't come out and get blown all over the place. We also need to attach it to a piece of square tubing. Normally we'd make a curved cut with a fish mouth cutter, but I don't have one of those, so I'm using a CNC mill to give it a nice fit. Next we'll start machining the shaft. We don't want any wobble, so we're being very careful how we do it. Supporting at each end helps, but even then it starts cutting on one side, which tells us how imperfect the material is to start with. But eventually it trues up just fine. We also need threads to hold everything together and adjust bearing clearance. Cutting threads on a manual lathe is nerve-wracking and easy to mess up, but these actually came out really nice. Of course, we'll need nuts to fit those threads, so we're making them out of a piece of bar stock left over from another project. That's a huge advantage of doing your own build. You get to design parts based on the materials you have available. The inside thread of the nut is made just like the one on the shaft. One pass at a time with a boring bar until the mating thread goes right in smoothly. After one more pass on the outside, it's time to head to the mill. The fourth axis is really handy for making the hex shape of the nut. Once done, it's back to the lathe to split off a piece to act as the lock nut so we can eventually tighten the two together. We're eventually going to need some way to adjust the height of this thing, so I'm grabbing an extra piece of square tube before welding it all together. I know the welds will distort the nice machined hub, but there's not much I can do about it without a second machining step, and ultimately, I don't think it will be all that bad. Once it's had a chance to cool, we can finally try assembling everything to see if it all worked out. Check it out! This is the first taper roller bearing setup I've ever designed, certainly ever built, and it actually looks like it went together pretty well. And of course now I have these two nuts on the back that I can use to cinch up the bearings to exactly the amount of play that I want, and then use that lock nut to lock the sucker down. So man, that should hold up to anything we're going to do to it with the wind. Alright, on to the next part. The generator is really heavy, so we need a substantial mount to secure it while driving down the road. I can't seem to find the bolt hole locations anywhere online, so I'm having to settle for taking measurements and approximating the best I can. For the two front mounting holes, I'm drilling them in the mill, but for holes between welded parts, I like to wait until all the welds are done before doing any machining. I seldom get to do much welding anymore, so this is a great opportunity to brush up my skills. Before going any further, I want to check the fit of the generator, which looks like it worked out great. One last thing I need to do is weld on some nuts for adjusting belt tension, and we'll be ready to check out the final assembly. Wow, I think there's a time for every engineer that designs something, and it's easy to use the math and the spec sheet and just pick what you need. But as soon as it starts showing up, things start getting real. That's what's happening with this. This is impressive. But I want to take this opportunity to talk about pulleys and gear ratios, because from the comment section on the Rain Gutter series, it's clear to me there's a lot of people out there that have a misunderstanding of what pulleys and ratios are for. So if you look at this, we have this huge pulley up on top versus the one that's on the generator. And it's actually exactly 3 times the size, or has 3 times the number of teeth as the one on the bottom. And what that means, of course, is as we rotate the turbine shaft for one rotation, you can watch the generator shaft go through 1, 2, and exactly 3 rotations. So whatever speed the turbine shaft is rotating at, the generator shaft is going to rotate 3 times that speed. But let's imagine for a minute that the pulley on top isn't any bigger than the one on the bottom. Let's say they're exactly the same size. Then the turbine shaft would be rotating at exactly the same speed as the generator, and we'd have a 1-to-1 ratio. But regardless of what ratio we have, let's say we took this thing out, mounted it to the truck, and we start driving around, and we're not getting the power output that we think we should. It might be natural to think, hey, well, if we just increase the size of the pulley on the turbine shaft, then that'll make the generator turn even faster and we'll get more power that way. But that's not correct. And I want to dive into it right now and show you why. The job of the belt is to transmit the same tension force across both pulleys. Now, if we picture each pulley as a lever, which one would be the bigger lever? The bigger pulley, of course. Well, leverage is just another word for torque. And torque is equal to force times distance, which in this case is the force of tension in the belt times the radius of the pulley. Since the lever of the big pulley is 3 times the lever of the small one, then we can say it has 3 times the torque. And you can feel the difference when you try to turn the shafts by hand. This large pulley makes the upper shaft difficult to turn, while the lower one feels super easy. And that's because we're turning it directly at a lower RPM, which takes less torque. To see how changing the ratio doesn't affect power, let's say the wind turbine can produce a torque value of 9 at a rotational speed of 100. And just forget about the units for now. Since the formula for power equals torque times RPM, we could multiply 9 times 100 and get 900, let's call them watts. But that's just the turbine shaft. If our pulleys were the same size, we'd have a 1-to-1 ratio and we'd be spinning our generator with 900 watts of power. But now let's see what putting this giant pulley on the turbine shaft would do. Like we said at the beginning, the generator will spin at 3 times the speed of the turbine. But what about our torque? Well, the lever on the smaller pulley is 1/3 the size of the big one, so we have to divide the torque by 3. Now watch what happens when we multiply to get the power. 900 watts? Hey, it's exactly the same. And that's what I said at the beginning. Pulleys and gears don't add any power. So why do we even bother with this giant pulley up here? Well, this generator is designed to run at 3,600 RPM, and this turbine is not. Now, honestly, I don't know what speed this thing is designed to run at, but I want to keep it and any future turbines at around 1,000 RPM, and this 3-to-1 ratio will do that. Now, I am just dying to get this thing out on the truck for a test drive, but first we need to change out some of the electronics. The turbines we've tested so far were all three-phase AC, which required a bunch of extra junk just to get to DC, then back to AC, but we're ditching all of that. Our new generator is single-phase, so we can connect it right to a heating element using a variable transformer. I'm trying a water heater element since I had one lying around, and building them out would allow me to try out my new press brake. Also, milling threads on a machine that was made in the 60s always makes me smile. It would have been impossible back then without a computer to follow a helical path. All right, we're going to test out this heating element and see. It's a 220 heating element. I've only got 110 plugged into the Variac, but I want to see if this display is supposed to come on at 80 volts AC. Let's see if that's actually the case before we have to go do this on the road with the truck. So here we're turning on the Variac. Okay, so 30 doesn't work. Just came on. 35 volts. Sweet. That's way better than the specs. The Variac variable transformer is 2,000 watt. It says max 20 amps. So let's see if that's the case. 700 watts. There's 1,000 watts right there. And oh yeah, you can feel the you feel the heat coming off of that heating element. Awesome. That should be good enough to go try this on the truck. Oh, is that thing glowing? That's actually glowing. Wow, look at that. That thing is glowing red. Yeah, it's a water heating element. It's supposed to be immersed in water. So we're going to go ahead and shut it down, but this should be good enough for our test. Okay, here we are. We have our new 7,200 watt generator connected to our 5-blade, supposedly rated for 500 watt wind turbine. And we were only getting a couple hundred watts previously, not even that, but we're going to find out, was that limit this turbine or was it the actual generator itself? I'm not optimistic about this flimsy plastic thing. The amount of torque that this thing has to deliver from the wind to be able to drive this generator at any decent RPM, I think is beyond what this plastic is going to be able to hold up to, but we're going to give it a shot and find out. We'll start out with no load on it at all and see what kind of rotation we can get, if any, and then go from there. What do you think? How fast are we going to have to go for it to spin? Come on, sucker, rotate. It's not even turning. There we go.
Finally. Not quite 35 volts yet. Whoa.
What? The speed?
Yeah.
Yeah, 500 RPM. Wow. So that's nice. We got 500 RPM just by going 40 miles an hour. So it's actually capable of spinning it. That's awesome. Now that we got it going, go ahead and turn on the Variac. Let's give this thing a shot. And then start turning it up and go to like 35, get to that 35 volts. See if you can get that display to come on. Oh wow, we're almost up at 1,000 RPM. Hey! Oh, I went and slowed down. Sorry. Go ahead. Give it a little more. Give it 40 or something.
I'm at 55.
You're at 55?
40 was when the display turned on.
Well, I guess go ahead and crank it a little higher then.
And the display's off.
Well, turn it up higher. How high is it right now?
The marker isn't on my side.
Oh, really?
That's how high.
It's still turned on, right?
Yeah.
That's weird.
Got it all the way up and the display still isn't on.
Okay, we'll turn it back down then. We'll figure out what's going on. Because it was working and now it's not. So I wonder what we did. Okay, we were getting some initial spinning on this thing and now it doesn't want to rotate anymore. I thought maybe there was something wrong with the generator, but it turns out that I probably didn't have the adjustment nut cinched down tight enough on my tapered roller bearings, and now even with the belt off, the thing does not want to spin hardly at all, and I didn't bring the tools necessary to adjust it, so we're going to head back to the shop real quick and we'll get this adjusted and come back out and give this another shot. But once we got back to the shop, I realized we don't actually have the right wrenches to fit those nuts, but we do have the means to make them. I thought about running the mill manually, but in this case, modeling them up in CAD and making a toolpath in CAM will only take a little bit longer and give a way better result. Now we can really torque things down so they don't give us any more trouble. Back to testing. Okay, so 378 watts is awesome because it's more than double what we've ever gotten before, but it's still a fraction of what the math says we should get. Now, why is that? Well, we can't generate more energy than is available in the first place, but we also can't produce more than the weakest link in the chain, and that weakest link right now is this turbine. Number one, it's not optimized for the wind speed we're using it at. Number two, take a look at it in slow motion. Normally the blades flex slightly towards the wind, but under load it's getting pushed back behind the plane of rotation. Sure, industrial wind turbines do this too, but they're designed for it while this one is not. Some have suggested the turbine is sitting in a cushion of air being pushed by the truck, but our instruments say that's not the case. Before the turbine starts to spin, the wind speed is pretty close to the speed of the truck. Once the turbine gets going, the wind speed behind it slows way down, telling us it's doing its job, taking momentum from the wind. Now, when I dive in deep to a topic like belt drives, a lot of viewers just leave because they came for entertainment, not education. They're so used to the sugar, they don't want any substance. And it's no secret, the videos with the highest views have almost no educational content. Ah! No! Now that leaves creators like me looking for other ways to support my efforts, and that's where Patreon comes in. Now, this series on wind power is my most expensive yet, and so far the ad revenue is not enough to cover the cost of materials. And that's where patrons can step in and help offset those costs when a video doesn't go viral. Now, if you're the kind of person who prefers substance over sugar, consider heading over to patreon.com/QuintBuilds to become a patron. There's no minimum contribution amount and every bit helps. And if you really want to dive deep, I have a second channel, Build 2, where I post real engineering content. There's a series called Wisdom from an Engineer, where I talk about working in teams and handling mistakes. There's also the most helpful math trick I ever learned and use most frequently as an engineer. I'm even making a video with real torque and power calculations for those that want to see it, so be sure to check that out. If the links aren't showing up here on your screen, check out the video description. But everyone likes a little dessert after a meal, so at the end of every video, I usually put an outtake or something silly as an incentive to watch to the end, kind of like movies do at the end of the credits, so stick around for that. Now the next thing we're going to do is what many would consider the black magic of wind power. We're going to learn how to design and build our own custom turbine blades. But fortunately, a number of you have reached out and told me about software that we can use to optimize the blade design. But I'm actually looking forward to it because remember, BUILD stands for Better Understanding Involves Learning and Doing. So we are going to get a way better understanding of how turbine blades work and what they do. We're also going to find out why we left a hole through the shaft of the wind turbine. And here's a hint, it's for an actuator. But that's all for now. I'm Quint with another one of my builds. Thanks so much for watching.
But the wind seldom does what we want, so I'm experimenting with